In this session, we look at the quality control. For any business, we need to ensure that the product or services we offer for sale are inconsistent with what we intended to offer. In other words, conforming to the specifications. In order to ensure the quality of conformance, one of the most popular tools we use for this kind of quality control is a statistical process control. That's what we're going to look at today.
Before we get started, let's try to clarify. There are two kinds of variations. Basically, first of all, variation is bad. We do not want our products vary too far away from the specification. Okay, we want them to be consistent. Okay, so when we try to understand the variations, we categorize them into two different variations. The first one, we call that a random variation, that it is created by some natural reasons or factors that is out of our control. That is nothing we can do about it. Okay. And we don't know what happens, so we have to leave it alone. Okay, so that's the part that is beyond our hand. There's another part of it that we call that assignable variation. That means we can identify the factors that lead to the variation. After we identify those factors, we can work on them. Okay. So the first random variations is something we cannot identify. There's nothing we can work on. The second is the one assignable. We have assignable factors, and then we work on the factors. What we want to achieve is to work on those assignable variations and make sure the products or service conform to specification. Here comes the example. Now suppose there is a manufacturing process. Each hour, this process produces a batch of 100 certain products. What we want to know is whether or not this manufacturing process is in control. So we're going to use some statistical sampling technique. Let's slow down here and look at this statistical process control technique step by step. So from one batch of the products, remember we have every hour there is a batch of 100 certain products been produced. Now we take one batch out of it, and out of this one batch we take 5 units. Okay, we call this sample 1. So from one batch we take a sample. Within the sample there are 5 units, and the measure of these 5 units are in the first column. Then we repeat this sampling process. Basically, from another batch, we take another sample. We call that a sample 2. In the sample, there are 5 units as well. So 1, 2, 3, 4, 5. And then we repeat this process again. We take the third sample. Notice that we can take as many samples as we want. Okay. Now, in this example, we take 3 samples. For each sample, we calculate the sample mean. What is a sample mean? Sample mean basically is the average of the sample. For example, in sample 1, the average of 95, 94, 93, 95, 95 is 94.4. In sample 2, the average of this five measures, the average is 96. Sample 3, the average is 94.8. If we repeat the aforementioned process many times, and what we do is we plot them above this x-axis. Okay, we plot the values of x bar. It will look exactly like this, the highlighted area. Why so? This comes from a statistical theory. Statistics theory, that is the central limited theorem, tells us that if we take a lot of those samples and if we plot the x bar, it looks like this. Now, what I mean plot here is the so-called dot plot in statistics. So if you need to review that part, please go back to the statistics textbook and search for the keyword dot plot. Now, the next thing comes from statistics as a central limit theorem. We're not going to repeat the central limited theorem here. What do we need to do is just to take it as a given, and we know that it looks like this shape right here. So this is a normal distribution. Now, for any given sample, remember we have 3 samples, right? In our example, we take one of it out. Now, if the x bar, which is the sample mean, fall in between 2 points, okay? What are the 2 points here? One is, we call that lower control limit, LCL, and the other one is upper control limit, UCL. Now, if the value of those x bar from that specific sample falls in between these 2 points, which means basically in this highlighted area, we call this particular sample in control. In other words, we're saying that this sample means stay close enough to specification. If a sample mean x bar falls outside of this 2 points LCL and UCL, we say it is out of control. And in other words, the x bar stays too far away from the average. It's inconsistent with the specification. Later on, we can turn this normal distribution around. So we turn it at 90 degrees, turn it from horizontal to vertical. It will look like this. And we need to show that in the run chart. For now, let me just say that if we turn it around, it still works the same way. Just don't get surprised when we something from horizontal to vertical. Recall that we have in our example, we have 3 samples: sample 1, sample 2, sample 3, with the sample mean 94.4, 96, and 94.8. That's the sample mean, okay? Our 3 samples in our example. So we can draw 3 axes. For sample 1, we can draw a axis right here, and we mark 94.4 here. Sample 2, we mark 96 here. Sample 3, we mark 94.8 here. Basically, this vertical line is the axis. Remember, from central limit theorem, we know that a sample mean x bar follows a normal distribution. So we can draw a normal distribution above this axis. Another normal distribution for sample 2 above the axis for sample 2. Another normal distribution here. And this line will be the upper control limit. This line will be the lower control limit. Okay. Now what we're doing is we need to make sure that all those red dots are within this UCL and LCL. We call that in control. If it is outside of these two lines, we call it out of control. In order to understand the situation better, this is another example. Now we have UCL, we have LCL, we have many samples. Okay, many samples. These are the sample mean, are the dots. And we draw those dots, and we're trying to find if the process is in control or not. Okay. Now, if the process is is in control, then all the dots should be in between UCL and LCL. However, we find there is a dot right here that is above the UCL line, so we can conclude that this process is out of control. So now we understand about the mechanism of statistical control technique. You probably start to wonder, how do we get the value for UCL and LCL? Now, there are for x bar, for the sample mean, sample average, here is the formula. UCL equals to x bar plus A2 times R bar. LCL equals to x bar minus A2 times R bar. Let me go through an example and show you how to use this formula. Now, in our previous example, we have 3 samples. Okay, and in each sample there are 5 units. So we take the average sample mean, which is highlighted in this blue. Basically it's the sample average. We also call it the sample mean. The other one we calculate is the sample range. Sample range equals to maximum number in the sample minus minimum number in that sample. So the maximum here is 95, minimum here is 93. So 95 minus 93 equals to 2. Okay. For sample 2, the maximum is 97, the minimum is 95, 97 minus 95 equals to 2. For sample 3, the maximum is 97, the minimum is 92, so the range is 97 minus 92 equals to 5. That's the range. Then the next we calculate the grand average. Grand average basically is the average of average, so we call that a grand average. For the average of average calculated this way, we take the average of the sample mean x bar here. So we take the average of these 3 numbers, and that average gives us a number here, which is the grand average, that is 95.7. The range here has an average as well. We call it R bar. R bar basically is the average range, and it equals to 2 from here, 2 from here, and 5 from here, divided by 3 equals to 3. So now we are ready. We have two numbers. One is grand average. The other one is average range. So we have X bar, the value of X bar, and the value of R bar. We also need a number we call that A2 from our formula. So in table 10.3 in the textbook, we have a factor for we can find the A2 value for 3 sigma. Now, this one, the factor for X bar chart is in this column. So this is what we're using right now. And we first look at the number of observations in subgroup, in each sample basically. Subgroup here means a sample. Now we have how many units in our sample? 5. So we know that n equals to 5. Okay. Now we look at this column here, first column. We look for where the n equals to 5. It's right here. So we look for the number in the corresponding column for A2, which is here. Then our value for A2 is 0.058. So what we found from this table is A2 equals to 0.58. Now let me put this X bar control chart for UCL and LCL here. Again, it is copied from the previous slide. It's exactly the same thing. What we need is to plug in 3 numbers here: X bar, R bar, and A2. We found this 3 numbers. And then we plug in those 3 numbers to this formula. We get UCL equals to X bar, which is 95.7, plus A2, which is 0.58, times R bar, which is 3. So this one equals to 96.81. We can also calculate the LCL. We found the value for UCL and LCL now. So we know UCL equals to 96.81. LCL equals to 93.33. So we draw 2 lines here. Okay, sample 1, for sample 1, the value is 94.4. So it is in between 96.81 and 93.33. Then the sample 2 average for sample 2 is 96. So it's in between these 2 values as well. Sample 3, 94.8, is within these 2 values, LCL and USL as well. So we can conclude that in our example, which has 3 samples, and in each sample there are 5 units. That's basically what the sample example we're looking at here. This process is in control as far as we can tell. So far we have learned how to use the statistical tools to calculate UCL and LCL, and then we can evaluate whether or not the sample means are under control. In other words, whether or not the average are under control. We can also evaluate whether or not the range of samples are under control or not. So here's the formula. This formula is like this: UCL of the upper control limit of the range equals to D4 times R bar. lower control limit equals to D3 times R bar. Now, we calculated R bar already in the previous example, so we're going to use that directly. And we need to find out the D3 and D4. We're going to use the same table, which is table 10.3, to find D3 and D4. D3, the values for D3 is in this column. The values for D4 is in this column. Now, we first, again, use the sample size, which is n. We have 5 units in each sample, so n equals to 5. Okay, and we look for n equals to 5, and in the corresponding column where n equals to 5, the D3 equals to 0. When n equals to 5, the D4 equals to 2.11. So from this table, we know D3 equals to 0, D4 equals to 2.11. Now, for convenience, we put this formula above here for convenience. So this is for R chart, the range control chart. Now, the UCL equals to D4 times R bar. We know R bar from our earlier calculation. R bar equals to 3. So UCL equals to D4 times R bar, which is 2.11, times 3 equals to 6.33. LCL equals to D3 times R bar, which is 0 times 3 equals to 0. Now we draw two lines, UCL and LCL. UCL equals to 6.33, LCL equals to 0. We know that our range, in our example, the ranges are sample 1 to sample 2 to sample 5 to 5. Now this 2 is roughly here for sample 1, sample 2 is here, sample 3 is here. So we know that the range for this process is under control. If there's anything goes beyond this line, which is somewhere here, or under this line, somewhere here, then the process will be determined as out of control. Now, when we have a process established, and after a while, when we are able to determine that this process is stable, the next thing we need to do is to determine if the process is capable of producing the products or services that is within acceptable range. So here's how we do it. If we go from the middle, which is the process mean 3 sigma to the right, 3 sigma to the left, so it will be plus minus 3 sigma. If this is the specification of the process, okay, now we will have 1,000 in this area, goes from this line to all the way to the left. Then the other one is the probability that the parts we produce will be smaller than specification. How many? It's 1,350. Goes beyond this line is the size here under this curve above this line is the probability that the parts we produce will be bigger than the specification, and the chance is 1,350 per million. If we go from the middle, 6 sigma to the right hand, and from the middle, 6 sigma to the left, we have plus minus 6 sigma. In this case, we'll have 1.7 per million part will be smaller than the specification, and another 1.7 per million will be bigger than the specification. We introduce a process capability ratio. The calculation is very simple. It is the specification width divided by the process width. So specification width is the upper specification minus lower specification, and process width is 6 sigma. Let's try to use an example to understand it. Now let's use an example to understand this process capability ratio. We have 3 machines, A, B, and C. And for machine A, the standard deviation is 0.13. Machine B, the standard deviation is 0.08. Machine C, the standard deviation is 0.16. Now, the machine capability here, we use 6 sigma, which is pretty much the standard today in the industry. 6 sigma, so 6 times the standard deviation, which is a sigma. So 6 times 0.13 equals to 0.78. 6 times 0.08 equals to 0.48. 6 times 0.16 equals to 0.96. The question is, we want to know which machine are capable if the specification are 10 millimeter to 10.8 millimeter. Now 10.00 basically is the lower specification, 10.80 is the upper specification. So now we're ready to plug in numbers to the formula. The formula is like this: upper specification is 10.8. Lower specification is 10 divided by 6 sigma, or machine capability. We know that machine capability equals to 6 times standard deviation. So 10.8 minus 10 equals to 0.80. So for the machine A, we do 0.80 divided by machine capability 0.78 equals to 1.03. For machine B, the value here is 0.8 divided by 0.48. 0.48 comes from here, the machine capability. Then it equals to 1.47. Now for machine C, it's 0.8 divided by 0.96. 0.96 comes from here, it equals to 0.83. So we know that 3 process has different capability. The A is 1.03, B is 1.47, C is 0.83. So the rule is, if the CP value here is smaller than 1, we do not think that a process is capable. So C is not capable. Okay. B is 1.47, A is 1.03. Both of them are capable, but B has a bigger process capability. So 1.47 is bigger than 1.03. So the machine B is the most consistent one with the highest capability of the process. This one probably is the one we're going to choose if we only consider process capability, and we leave other things, for example, the cost and other factors alone. So this one, in terms of process capability, it is the best. There are different ways to improve the process capability. We can do simplification of the process, which make it easy to maintain, easy to identify problems, and easy to improve. And we can do standardization. Standardization is another technique, and some other techniques. Now, please go ahead and read the textbook after you understand this statistical side of this. Please read the chapter 10 and try to learn more about process capability, especially how to improve process capability.